This will be the last video on integration by parts, and I'd like to use the opportunity to talk about a formula that may be useful to you if you are differentiating functions like sine to the power of nx, cosine to the power of nx, natural log to the power of n, and many other functions that are raised to the power of n. Generally, with the reduction formula, you reduce the integral from a power of n to a power of n minus 2. So that tells me that if I carry out this again, I'm going to have like n minus 4, n minus 6, and like that. Eventually, the integral becomes like integral of just x if n is odd, or integral of integral of sine x if n is odd, or integral of 1 is if n is even. So with that, let's try to prove this formula first. I would like to split sine x to start my proof. Generally, this is like how this proof is done. It's not like we're using any special trick. So I'm going to write sine to the power of nx as sine x, or sine to the power of n. Start again. Sine to the power of n x dx. I'll factor out one sine, so I'm going to have sine to the power of n minus 1 x sine x dx. And then here you may ask, like, why are we using integration by parts? Well, we only have sine, so we are just going to make our choice of hue the way we should to make our life easier. Well, I know if I differentiate my sine to the power of n, it's likely going to give me something simpler. So I'll do that here. Or maybe, let me do it below. I'll let my u to be equal to sine n minus 1x, and then my dv equal to sine x dx. Now notice that it's going to be very difficult for you to integrate sine to the power of n minus 1, but you can easily integrate sine x. So that is why we chose dv to be this. And this implies that if I differentiate u, I'll get, this is like power law of differentiation. So first of all, I'm going to get n minus 1 multiplied by sine of n minus 1, which is minus 2 of x, and then differentiating sine x gives me cosine of x. I use power law of differentiation here. And if I integrate dv, if you integrate sine, you get negative cosine of x. Actually, there is a dx here. Now, by integration by parts, my integral of sine nx dx, which I split up to be the integral of sine n minus 1x sine x dx, would be equal to, my uv would be negative cosine of x, which is my v, sine of n minus 1, sine to the power of n minus 1 rather, x, then minus integral of v is negative cosine of x, and my du is n minus 1 sine n minus 2 x cosine of x dx. This would be equal to negative cosine of x sine to the power of n minus 1 x, minus here is going to give me plus, so I'm going to have plus here. Integral of cosine multiplied by cosine is going to give me cosine squared of x, and then sine to the power of n minus 2 of x dx. I'd like to do something here. I'd like to, since I'm working with x, I'd like to change this cosine squared to sine. Recall that cosine squared plus sine squared is equal to 1. So cosine squared is equal to 1 minus sine squared. If I make that change or substitution, I'll get this. N minus 1 to the power of plus integral of, instead of cosine squared, I'm going to write 1 minus sine squared of x, and then sine to the power of n minus 2 of x dx. Next, I'll split that difference. Plus, I'll split that difference. If I split the difference, I'm going to get 1 times this is just sine of to the power of n minus 2 x, and then sine squared minus here. Sine squared times sine to the power of n minus 2 is just going to be sine to the power of n, because the power will be n minus 2 plus 2, which is just n. So I'll have sine to the power of n x dx. Now recall that, okay, before I say that, let me just split the integral. So I have cosine of x sine n minus 1 x plus, if I split this integral, I'm gonna get oh, I think I left something behind. I left n minus 1. Okay, I'm gonna squeeze it in here. I'm gonna squeeze that in here. Sorry about this error. So I have n minus 1 here plus n minus 1 plus here n minus 1. Right. Okay. So if I split that integral, I'm going to have plus n minus 1 integral of sine to the power of n minus 2x dx minus n minus 1 integral of sine to the power of nx dx. Now, why do I need this here? Well, this looks like the integral I started with already. So what do? I'll just carry this integral to the left hand side and add 2 of them together. If I do that, I'll have that this integral implies on the left hand side I already have integral of sine to the power of nx dx, and then I'm bringing this term here to the left hand side. If you notice, it is negative. So if it goes to the left hand side of this equation, it becomes positive. I mean this to left hand side. So that would be positive plus n minus 1 integral sine of n here. And then on the right hand side, I have negative cos x sine of n minus to the power of n minus 1, and then plus n minus 1 integral of sine to the power of n minus 2 of x dx. Now over here, I would be having, if I factor out sine of n minus 1, so I'm going to have, like, let me open up a bracket and have integral of sine of to the power of n x dx. What I'm going to have from here, just get 1 as the factor, plus from here I get n minus 1. 1 plus n minus 1 is just going to give me n. So on the left hand side of this equation, I'll be having n sine this is equal to whatever is on the right. I'll still write that down, though it becomes more repetitive, but it's okay. Plus n minus 1 integral of sine of n minus 2 x dx. Finally, because I'm just looking for integral of sine to the power of n x dx, then I'll divide both sides by n. If I divide both sides by n, I have that my integral of sine to the power of n x dx let me write this better so that power and sine are distinct enough. Sine to the power of n of x, maybe put this in brackets to make it look better. Hope it is. It's equal to minus 1 over n over here, because we are dividing by n, cosine of x sine to the power of n minus 1 x plus n minus 1 all over n integral of sine to the power of n minus 2 of x dx. And this formula is called the reduction formula. We've gone from an integral of sine to the power of n to an integral of sine to the power of n minus 2. So here is the formula, and we proved it. Actually, we have this formula for other different functions. So let's see how we can use this formula. Well, I'm going to write that formula maybe, where can I write it? Let me write it at the top here. Integral of sine to the power of nx dx is equal to minus 1 over n cosine of x sine of n minus 1 x. Please pardon that x is too far from where it should be. Integral of sine to the power of n minus 2 of x dx. Just to recall the formula. Now over here, we have that usually the reduction formula just helps us to use it repetitively to reduce sine of nx to the power of n of x, and then until we get sine x if n is odd, or we get just this integral if n is even. Here n is odd and my n is equal to 5. So by the reduction formula, you can use this formula maybe in an exam or your homework, but if you use it, you have to quote that that's what you're using. N equal to 5, so my integral of sine to the power of 5 of x dx is going to be equal to minus 1 over 5, which is minus 1 over n, cosine of x sine to the power of n minus 1 is 5 minus 1, which is going to be 4x, plus n minus 1 over n will be 4 over 5, integral of sine of n minus 2. 5 minus 2 is 3, so I'm just going to have sine cube x dx. I'll apply that formula again here, sine cubed for n equal to 3. If I do that, I'll get that this will be minus 1 over 5 cosine of x sine to the 4th of x, plus I'll have 4 over 5 outside, and then I apply that formula again here. If I apply it again here, I'm going to have minus 1 over 3 cosine of x sine of n minus 1 is 3 minus 1, so that's going to be 2x, plus n minus 1 over n is going to be 2 over 3 integral of sine of n minus 2. 3 minus 2 is 1, so I'm just going to have like sine x dx. Finally, this will be equal to minus 1/5 cosine of x sine to the power of 4x plus 4 over 5 into negative 1/3 cos x sine squared x. If I differentiate or integrate cosine, I get negative sine. Or if I integrate sine, I get negative cosine. So this is going to be like negative 3 over 2, or 2 over 3 rather, cosine of x. And then plus a constant. Usually I write my constant outside so I don't start working with too many constants. If you simplify this, you get an answer, but basically this is the integral of sine to the power of x. Let's look at a simpler example. Here, applying that formula with n equal to 2 by reduction formula for sine. Let's look at the formula again here. It says it's negative 1 over n cosine of this, sine of this, and whatever. I think I should have that. So integral of sine squared of x dx is going to be equal to minus, my n is 2, so I'm going to have 1 over n, which is 1 over 2, cosine of x. Sine of n minus 1 is going to be like sine of 2 minus 1 is just sine x, and then minus n minus 1 over n is going to be 1 over 2 integral of sine of n minus 2. 2 minus 2 is 0 of x. This is just something as sine x raised to power 0, which is 1. So I'm just going to have 1 here dx. And this would be the same thing as minus 1/2 cos x sine x minus 1/2 x plus c. Now, usually cos x sine x by half angle formula is 1/2 sine 2x. So this can be written as negative 1/2 cos x sine x is something as 1/2 sine of 2x by half angle formula, then minus 1/2 x plus c. So this will be the same thing as negative sine of 2x over 4 minus x over 2 plus c. And this becomes the integral of sine squared. In the next section, 7.2, we'll see how to do this integral another way. But even if you do it that way, you're still going to get the same solution here. So we've seen how useful integration by parts could be. I hope you notice when you use it if you are given an integral to evaluate. In the next video, we'll begin a new section, trigonometric integrals. But before we go to that video, let me see, I think I may have one or two things to say about reduction formula. Now look at this table here. This gives us a list of some reduction formula for n is greater than 2. This is the formula for cosine. Looks pretty much like sine except with the negative value here. And this is the sine, the one we proved already. This is for the natural log. This is for function that will occur in this form, x to the power of n e to the x. You can use this reduction formula. Tangent of this should be tangent to the power of n here. And then x dx is equal to this. And secant to the power of n has this reduction formula. All these things can be proved using integration by parts. I'd like you to try to proving them at your own convenience. We've proved this already. Maybe another one you can try is this, to prove this by reduction formula. It will be very useful if you can. And this one also, it will be useful if you can. I think we saw an integral in the form t squared et dt, and you can actually use this formula here to do that integral. Okay, so this brings us to the end of section 7.1, integration by parts. Next, we'll look at trigonometric integrals.